Heat is the transfer of energy between objects of different temperatures. The three well-known methods of heat transfer are conduction, convection, and radiation. Conduction is heat transfer between objects which are in physical contact with each other and is a result of collisions of moving particles. An example of this is your hand on a warm cup of coffee. Convection is the transfer of heat through movement of fluids like boiling water in a pot. And finally, radiation occurs when electromagnetic waves are emitted and absorbed, like heat from the sun. These three methods of heat transfer were decidedly the only ways that thermal energy could be transported. That is until recently. In the past decade, there has been more and more evidence to prove the existence of a fourth, previously unknown method of heat transfer. But in order to explain this process, we must first understand the Heisenberg's uncertainty principle, quantum fluctuations, and the Casimir effect. Heisenberg's uncertainty principle quantifies the uncertainty between two operators in a quantum mechanical system that do not commute. Position and momentum are the best known examples of this. The position and the momentum of an object cannot be measured at the same time with any precision. This inequality states that the uncertainty in measuring position multiplied by the uncertainty in measuring momentum is greater than or equal to some constant, meaning that as measurement of one operator becomes more certain, the uncertainty in measuring the other increases, so the more you know about one, the less you know about the other. The operators we are concerned with for this topic are energy and time, whose measurements behave in a similar way. If you know how much energy a particle has, then you can't know for sure how long it has that energy. A corollary from this is that there is a large uncertainty in the energy of a particle that exists for a very short amount of time. A large uncertainty such as this means that a particle can have no energy, in other words not exist, or it can have some energy greater than zero and exist. But there is no way to distinguish between these two possibilities, meaning they are equally probable. So, it is possible for a particle with a certain energy to come into existence from nothing, with no cause, so long as they exist for very tiny amounts of time. These virtual particles always come into existence in pairs and will consume or annihilate each other within a time defined by the uncertainty principle. These particles popping in and out of existence create quantum fluctuations, which happen anytime, anywhere, even in a vacuum. This all seems impossible, that particles can be created out of nothing and that vacuums aren't actually empty, but rather a seething mass of virtual particles. But in fact, this is very much what is happening on a quantum scale, and this can be observed through something called the Casimir effect. If you have two uncharged conductive plates in a vacuum and put them close together, about a micron apart, there will be an attractive force between them, pushing them together. This force can be measured and can only be explained by quantum fluctuations. But where does this force come from? Virtual particles will come in and out of existence everywhere in the vacuum, and when the particles collide with the plates, a force will be exerted on them. Because of the confined space between the plates, the particles that can exist there must be smaller than what can exist everywhere else in the vacuum. This means that there are fewer particles that can exist in between the plates than on the outside of them, which creates a greater pressure on the outside of the plates than from the inside, pushing the two plates together. Now that we have an understanding of these concepts, we can revisit the new method of heat transfer, which happens in a vacuum as a result of the Casimir effect. We know that heat is carried through vibrations of atoms, so heat can be transferred between objects through vibrations, which are known as phonons. In February of 2019, researchers proved the existence of phonon heat transfer across a vacuum due to quantum fluctuations, and this is how it works. Similar to the setup for the Casimir effect, you have two uncharged conductive parallel plates in a vacuum, but this time one of the plates is heated to a temperature greater than the second. The difference in temperature indicates that the atoms in the first plate are vibrating faster than the atoms in the second plate. The Casimir force, which is acting between the plates, can then act as a coupler to transfer phonons from the hotter, faster vibrating plate across the vacuum gap to the second plate. These phonons interact with the second cooler plate, causing it to vibrate, changing the temperature of the second plate. And that's heat transfer. The researchers used several methods to ensure that this transfer of heat is distinct from heat transfer through radiation or electrostatic transfers and proved that it was something totally different. This means that there is mounting evidence to suggest that heat can be transferred in a new way across small gaps in a vacuum, thanks to quantum mechanics.